All right, hello everybody. We'll go ahead and get started here on this webinar for the Safety Through Disruption University Transportation Center. Today, Greg Griffin is going to be delivering the webinar, telling us a bit about his work on street noise relationship to bicycle road user safety and its practical implications and next steps. Greg, with that, you want to take it away?
Certainly. Thanks so much for the introduction. Again, my name is Greg Griffin. I'm currently at the University of Texas, San Antonio as an assistant professor, but I was with Texas A&M Transportation Institute along with Chris Shemek, a co-author on this project. But I do want to point out that a co-PI on this project was Steve Hankey at Virginia Tech, of course, with a lot of additional work also by Hugh-Yen Lee, who also was a PhD student at Virginia Tech and now an assistant professor at The Ohio State University, and also with guidance of Ralph Buehler as well. So again, I'd like to thank Safety Through Disruption University Transportation Center for their sponsorship and support of not only the research, but also this webinar series. And with that, I'll get underway. If I can advance the slide, there it goes. So overall, I want to introduce this whole concept of how we started to address the topics of street noise and vulnerable road user safety, which we specifically looked at bicyclists. And then take a look at some of our initial findings from the Washington, D.C. capital area and also Austin, Texas. But focus a little bit more on the practical implications, sort of what this means, in addition to discussing next steps. So I wanted to preface all this by stating that I got interested in this because of personal experience. As a bicyclist on Texas streets and highways, street noise is something that you can't ignore, but it often left me wondering if it makes you feel uncomfortable while you're biking, which I can at least offer. Is there also a relationship with if it's actually unsafe? So that was the concept and where we wanted to begin with this study. I'll see if I can share a little bit of street noise with you. If it makes noise. So biking down a street, whether that's a busy arterial or a highway on the edges of town, street noise, at least through passing vehicles, can be startling, in addition to potentially be related to actual danger. However, that concept has never been tested before, so that's what we wanted to take a look at. Previous studies related to crash risk tell us some pretty intuitive relationships where when we do have low traffic roads and separated paths, we generally have a lower rate of bicycle crashes. That's intuitive based upon the protection of the bicyclist, but also speed differentials that you might experience, which could also be related to safety issues. The second main point from previous work is the safety in numbers hypothesis, where you have both with bicycling and with walking. Whenever you do have streets that have a higher volume of activity, they also often show a lower overall risk for crashes. And that's been, there's several different ideas for why that might be true, but it's not comprehensively solved yet. But many people think that for one thing, it could change driver expectations and behaviors on roadways where they often see bicyclists and pedestrians. But there also could be other factors as well, where the physical proximity of bicyclists and pedestrians may change the geometrics of how the road operates a little bit as well. However, again, we could not find any research that directly looked at the relationship between bicycle safety risk and street noise. So to be a little bit more specific about what it was that we were looking into, we thought we'd separate out these questions into two groups. First is understanding that overall relationship, a quantitative relationship between street level noise and crash rates as experienced on the bicycle mode. And then second was the relationship between like the design of the street and land use variables that might be associated with relatively high or low street level noise rates. So to look at this issue, we collected data on the streets. I started testing a smartphone application called NoiseTube that had been previously used, that was developed in Europe for geolocating noise volumes on an ongoing basis. So you can basically track a route, like you might with a phone application like Map My Run or Strava or something like that. But this also records the noise levels in A-weighted decibels specific to each GPS location. So we might suspect that smartphones are not necessarily the same quality of recording as a reference quality meter. So Texas A&M Transportation Institute did have a noise meter that I could use as a reference. And so on over 10 locations in Austin, I recorded noises, sound levels in the street context from both the reference meter and the smartphone simultaneously, and then later compared. And we did find that those were comparable with some variation. I do think that most of the variation is due to the muffling effect that you have from wind noise based upon the foam muffler on a reference quality meter. So that'd be one potential improvement that we could look at for collecting noise via smartphone. However, I want to point out that the whole idea of this, I thought that if we had a strong relationship or something of value looking into further, I'd want a broad group of people to be able to undertake it. So it ought to be simple enough for planners and everyday citizens to be able to implement if they wanted to add to this kind of data set and look in their own issues, which may not be related to our specific topic of bicycle crash risk. Now, the third item there is that if we wanted to talk about actual crash risk as opposed to just the number of crashes, we also had to have bicycle volumes. For those of you that have looked into this kind of data for bicycling, it's not readily available. We don't have the same scale of bicycle volume data collected by transportation agencies that we do for automotive modes. So we used a model that was developed principally by Huyen Lee in partnership with their Virginia Tech team that was based upon a national level data collection effort of individual counts. And so I think most of those counts were 2-hour counts, but they were very numerous. And so it developed a direct demand model that we're able to apply in both Washington, D.C. and Austin. However, I must preface this to note that we did not have Austin-specific bicycle count data that was comparable with the other national level data that she wanted to use in that model. So it's not locally validated for Austin, but it was in the Washington, D.C. capital area. And then finally, in order to be able to explore this relationship, we started with the assumption that there's a spatial variation in both crash rates and noise levels. And so in order to be able to accommodate that, we took a spatial regression methodology that is able to weight levels depending on their location. In other words, observations that are near to other observations also influence them. So we're not just looking at the impact of one point in time. We're looking at other observations that are closest to those as well. So let's jump into the findings from both the capital area and Austin. And I write here DC, but I want to note that the capital area also includes Alexandria to the south. So, and Arlington, Virginia as well. So this is a map of our street noise levels that we actually measured. And so these are averages of multiple routes. We didn't just write it once. We rode each route over 10 times at different times and different days of the week to collect adequate data. So the data that you're looking at right here again is A-weighted decibels, which are aligned with the frequencies that can impact most humans. And so these figures that we're looking at are averaged at the segment level. In other words, what we might think of as blocks, but also including any cut-through streets, that's where those segments are broken into separate sections. So we can see that we have some long sections where we have trails in the route on the DC route on the right. And then further in downtown, both Austin and DC, we see some very short segments as well. So overall, the street noise levels were very comparable, but very slightly higher in Austin than in DC. Now, that doesn't mean, of course, that all traffic streets are louder in Austin, but rather the route that we studied. We couldn't, of course, have the capacity to study a huge area, but we did try to encompass a range of downtown locations and also suburban locations in each city, so that there's some comparability, but that's also why we report separate statistics between the two cities. We don't group everything together. So the average rates, or as we say, the notation on the left is the mean, M equals 79 decibels in Austin and 78.5 in the capital area. And so blue, of course, is the lowest or quietest areas. Red is the highest. If you look in Austin, we see a little bit more range than the values in DC. The big splotch of red up on the northern end is US Highway 290. And so there's a section of over 50-mile-an-hour freeway with a wide shoulder that I biked along. And so that's where you see that peak of noise. And I do also want to mention that when we collected this data, we didn't try to separate other street noises. That's why I call it street noise as opposed to vehicle noise. You might anticipate that most of the noise was likely created by the traffic volume on that street. However, we had no way to screen out other noises, and we wanted to encompass all of the noise that was present in that environment. And so we also see potential wind effects too. If you look over in the capital area in DC, where the path crosses the Potomac River, it is separated from traffic right there. But I think that we have a slightly higher decibel rating, potentially because of wind noise that you might pick up in that section over the Potomac River. So again, wind noise might have had an impact here as well. But when we look at crash rates, we have some interesting findings here. Of course, we definitely have hot spots in areas that have a high number of conflict areas. And so the red areas designate the crash risk as having annualized crashes of over 10 crashes per 100,000 bicycle kilometers traveled. And so again, we're normalizing by bicycle volumes. In the downtown Austin and area near the University of Texas at Austin, we see a relatively high crash risk as compared with others. But that isn't necessarily just tied to the frequency of intersections. If we look down in the Austin map on the left, in the lower and more on the right-hand side, that's a street called Pleasant Valley, which doesn't have very many street intersections at all. In fact, it's along a parkland on much of both sides, but all of the east side. However, that's a very minimal bicycle facility and narrow bike lane, and a lot of apartments and bicycle traffic using that route. And that's a spot where the city is now looking at another bridge option to create an alternative route for cyclists. Now in DC, we see much more of a clustered pattern. To the south in Arlington and Alexandria as well, we see a higher crash rate. But I do want to point out that a lot of that section where we have 0 crashes, that is that light tan color, was on a separated path. And so it's intuitive that the years that we looked at, which by the way was 2010 to 2017, so we included all the crashes several previous years, we did not have significant crashes that showed up in the police databases that we used in those areas. So an interesting finding here also is that Washington, D.C., despite perceptions of bicycle safety, actually was, when you normalize it by the actual bicycle kilometers traveled, much lower risk than a lot of the other areas in the DC area, but also from Austin. And that could be due to that safety in numbers hypothesis, but also the bicycle infrastructure that's been built out in the DC area. That could have an impact as well. So again, we ran some spatial regression and found that in Austin, we looked at street noise, but also normalized, or rather controlled for road classification and bicycle mode share in the neighborhood, that all those together did not have a significant impact on crash rate. Even separating out the issue of street noise by itself, it did not meet our threshold of a probability value of less than 0.05, but it was just outside of that. I think it was 0.09 for that issue. So it might have been marginal. It might have been something that we should look at more closely, but overall, it was not predictive of crash rate for those factors. However, in the DC area, we saw a very different relationship. The same factors using similar data sets combined did explain most of the variation in crash rate within the DC area. And specifically, the street noise variable also had a stronger both probability and correlation. However, one thing that was consistent between both is that regardless of statistical significance, the direction of the relationship between street noise and crash rate was the same. So wherever we had quieter streets, overall, we also had a decrease, a negative relationship with crash rates overall. So that was consistent. And this is more the specifics on the street noise. There's that p-value of 0.09 if you're into the statistics, where it wasn't significant. But we also looked at the relationship of noise and other characteristics as well. And going into some of the more specifics on our earlier hypotheses, this sort of spells everything out that we looked at specifically on these hypotheses. But let's sort of dig into some of the practical implications. What does this actually mean for planning, if anything? Again, this is just the first step. You might consider it a pilot study to collect this type of data and look at the relationship. So all this was exploratory in a lot of ways. Again, this was the first examination that we could find, specifically looking at street noise and bicycle crash risk. And this data, nonetheless, did find, specifically in Washington, D.C., that providing the infrastructure for bicycling, such as the separated paths and well-connected, lower traffic volume residential street, we did see a lower overall crash risk. And often that was related as well to street noise. And then second, we also did see, particularly related to our analysis of the bicycle mode share, we saw support for the safety in numbers hypothesis. Wherever we had areas with a higher bicycle commuting, mode share also had a lower crash risk. We found a negative relationship between those variables. Therefore, this provides additional support for improving bicycle infrastructure in cities. And in some cases, that might mean adding protected bike lanes, but in some cases that also can emphasize creating new parallel routes that have lower speeds and traffic volumes that might also be related to street noise. However, we collected data, of course, in only 2 cities and in select routes within those cities. So we do recommend that we collect additional data. not only within the existing cities, but also other cities, we may find other relationships that could either corroborate or they could conflict with our initial findings. And safety does have this entire data set available, and I'll point you to the website towards the end, but I want to encourage any researchers or practitioners who want to work with this data and take a look at the relationship in different ways to please work on that. The other is that we did not use a bicycle travel model that was tailored to each city. It was a national level model. And again, we did not have, we did not validate it specifically for the city of Austin. So that may have something to do with why we got different results related to crash risk. However, we thought that was a reasonable compromise to make, recognizing that we wanted to be able to address the issue of normalizing the risk by actual traffic volumes as best as we could. That was much better than not looking at the overall bicycling levels at all. And then third, we'd like to do additional tests related to specific street infrastructures. So we did not look at the specifics of, say, separation between a certain number of feet related to, bicycle traffic from car traffic related to different bike lane designs. So that would be an intuitive next step to look at this relationship as well. And additionally, of course, we're talking about the quantitative results on actual crash risk, but I think it'd also be interesting to take a look at the subjective perceptions of cyclists with street noise related to their experience of the street. And so again, this data set is available for different types of applications. So that sums up my presentation. Here's some of the references that we used in the study, and then I'll look forward to addressing any of your questions.
Thanks a lot. Sorry, thanks a lot, Greg. That was really helpful. So at this point, if you have a question, feel free to unmute yourself. You're all on mute, just a heads up, and go ahead and ask Greg verbally, or if you have any trouble with that, feel free to type as well, and I'll read them to Greg. I guess while we wait to see if anyone has a question, Greg, I've got maybe a couple here, but one thing I was going to ask is you sort of talked about various other aspects of cycling pathways and whatnot that might be related to crash risk or potentially other measures of sort of acceptance and whatnot, which got me thinking that there's a lot more, within a noise signal than simply amplitude. I was wondering if you had any thoughts about, how you might analyze the noise signal at a, more of a component depth in order to understand maybe some of those influences and, how
Right.
close a building is, for example, you might be able to detect that through a noise signature. Just wondering if you have any thoughts about that and where it might lead.
Yeah, there's a lot that goes into the factors of whether we consider noise to be, either calming or jolting or to cause some other reaction. So yes, you're right. There are many different components to sound that we could study as well. For one thing, with our specific methodology, I would anticipate that, using a smartphone with, off-the-shelf methods like we did probably would bump up against limitations of the hardware and software to be able to measure these kind of issues. And we'd have interesting challenges because we're talking about a moving vehicle. And so, like you said, the contextual issues of whether you're surrounded by buildings or perhaps having different types of noises muffled by trees nearby would have a differential effect, but it would also have a time-based effect as the cyclist is moving through that area. And so even looking at trying to decrease the number of things that were interacting on that relationship would be helpful. And so one of the ways you could do that potentially is by using static location recordings instead of moving. So I think you could better isolate what the context of that location is if you were to do static recordings, and potentially using reference quality equipment for that kind of a context. With this study, there's a lot of different, real environment factors that get muddled within the data set that we have. And so, yeah, it's not exactly a laboratory situation. It's quite the opposite. So a lot of different angles that you could potentially look at this from a research perspective.
Yeah, that makes sense. I guess I was assuming one of the potential, I guess, use cases or benefits is the possibility of crowdsourcing data real broadly and having sort of a very dynamic big data measure from cyclists who just happen to be running an app that, can run some sort of noise analysis in the background. Is that sort of what you saw as the primary motivator for, I guess, looking at this work on bicycles versus, using traffic density or other more traditional measures of, that might be better correlated, it looks like, to safety than what you found, at least at this early analysis?
Absolutely. So those of you that might have known of some of my other research, a lot of it relates to crowdsourcing. And so I'm interested in two issues for that. And one is collecting data that we wouldn't have otherwise, right? So we, of course, don't have a comprehensive database of street noise. So at first I wanted to test this method and see if this is even a potentially viable approach to be able to collect data. And if so, would it even match a reference quality equipment? And so in that way, I do think that this study validated the approach that you could adapt to be able to do a number of different noise-related studies in urban environments from this approach. The second, related to crowdsourcing, is also think of this form of data collection as a potential method for public participation, that is for citizens. Sometimes we call it citizen science. To be able to address issues on their own. So there might be issues with street noise that are in some locations related to people's health and well-being. That street noise is not just experienced in an instant, but for those that live or work in an area, experience it constantly. And so this could potentially be a method for citizens to collect their own data to be able to advocate for changes in their environment to improve issues related to street noise.
Yeah, excellent. So pausing here for a second. Anyone have any questions for Greg? Go ahead and unmute yourself or type into the box. Well, hearing none and seeing none, Greg, I think you might be off the hook.
Okay, well, thanks so much again for having me and getting to present this this research, and also to safety as an organization, but also for many of you that are also on the call. I do appreciate this partnership that we had to begin this type of work, and look forward to working with you all in the future.
Excellent, and likewise, Greg, appreciate the time you took. And we will have a recording up on the website here shortly so that you can guide other people to it and spread the word. Appreciate the hard work.
Thank you. Have a great day.
Absolutely. Bye, everybody.